Myself, Purvika. I'm going to speak about asymptotic analysis. Asymptotic analysis is an important concept used to study the efficiency of algorithm. In computer science, many algorithms are used to solve, but not all algorithms perform equally well. Some algorithms take more time while others take less time. Therefore, we need a method to analyze and compare the performance of algorithm. Asymptotic analysis helps us to understand how algorithms behaves when the input size becomes very large. This asymptotic analysis is a method of analyzing the time complexities and space complexity of an algorithm as the input size approaches infinitely. Instead of calculating the exact running time, asymptotic analysis focus on the growth rate of an algorithm. This means we study how an algorithm's running time increases when the size of the input data increases. Asymptotic notations are the mathematical tool used to analyze the performance of algorithms by understanding how their efficiency changes as the input size grows. This notation provides a consequences way to express the behavior of an algorithm's times or space complexities as the input size approaches infinitely. Rather than comparing algorithms directly, asymptotic analysis focus on understanding the relative growth rate of an algorithm's complexities. It enables comparison of algorithm efficiently by abstracting away mission-specific constant and implementing details focusing instead of fundamental trends. Asymptotic analysis follow the comparison of algorithm space and time complexity by examining their performance characters as the input size varies. By using asymptotic notation such as big O, big omega, big theta, we characterize algorithm based on their worst case, best case or average case time or specific space complexities, providing valuable insight into their efficiency. There are mainly three types of asymptotic notation: big O notation, omega notation and theta notation. We'll see this all three notations. Now, big O notation. Big O notation represents the upper bound by running time of an algorithm. Therefore, it gives the worst case complexity of an algorithm. It is the most widely used notation for asymptotic analysis. It specifies the upper bound of a function, the maximum time required by an algorithm, or the worst case time complexities. It returns the highest possible output value, big O, for the given input. Big O in the worst case, it defines as the condition that follows an algorithm complete statement execution in the largest amount of the time possible. In this diagram also we can see that it defines that if f of n describes the running time of an algorithm, f of n is o of g of n if there exists a positive constant c and n naught such that o is less than or equal to f of n, less than or equal to c of cg of n for all n greater than equal to n naught, and it returns the highest possible output value big O for a given input. The execution time serves as an upper bound on the algorithm's time complexities. In this we can see that the diagram which is having f of n is equal to og of n. Next, omega notation. Thus, omega notation represents the lower bound of running time of an algorithm, thus it provides the best case complexities of an algorithm. The execution time serves as a lower bound of an algorithm time complexities. It defines an condition that allows an algorithm to complete statement execution in an shortest amount of time. Let g and f be the function from the set of n natural numbers itself. The function f is said to be omega of g. If there is a constant c is greater than 0 and a natural number n naught such that c into g of n is less than or equal to f of n for all n greater than equal to n naught. Even the diagram is able to see, we can able to see. Next, the theta notation. Theta notation encloses the function from above and below. Since it represents the upper and the lower bound of an running time of an algorithm. It is used for analyzing the average case complexity of an algorithm, theta average case. You add the running time for each possible input combination and take the average in an average case. Let g and f be the function from the set of n natural numbers itself, and the function f is said to be theta of g if there are constants c1 and c2 is greater than o and a natural number n naught such that c1 into g of n less than equal to f of n and less than equal to c2 into g of n for all n greater than equal to n naught. Thank you.